Okay, the last concept we need to look at in our videos on complex numbers is curves, regions, rays, and arcs on the Argand diagram. So we can plot complex numbers in general, and often they represent lines and regions, especially with inequalities on the complex plane. So z plus z bar is greater than 4, for example. Well, for simple ones like this, it's nice and easy just to, and it always will work as a last resort, to replace z with x plus iy. Now we know z plus z bar from our conjugate theorem is 2 times the real component of z, which we've defined to be x. And that's greater than 4, which means x is greater than 2. So all we need to do is plot that on the complex plane, or our Argand diagram. Greater than 2, we're going to put a line at x is equal to 2. It's a dotted line because greater than 2 does not include 2. And we're going to shade, want a pen, we're going to shade there. Mz is 3 is just telling you the imaginary component of z is 3, which is just another way of saying y is equal to 3. We just draw the line y equals 3. Okay. 2 mod z is z plus z bar plus 4. Well, the modulus of z is found by going the square root of x squared plus y squared. We know that z plus z bar is equal to 2x plus 4. Let's divide both sides by 2. X squared plus y squared equals x plus 2. And square both sides, we get x squared plus y squared is x squared plus 4x plus 4. And that's y squared equals 4x plus 4. Now, I don't like that they still give questions like this in exercises and in the HSC and trials, because the new syllabus after 2020 got rid of a topic called the locus and the parabola, which part of it had sideways parabolas in it and defining parabolas parametrically. But all you need to know is y squared equals x is a sideways parabola with a y-intercept of -1 and x-intercepts of y-intercepts of plus and minus 2, because we make x 0 and then the square root of 4 is plus or minus 2. Okay, circles. The length of a vector from the center of a circle to any point has a modulus equaling the radius. So z bar equals r is a circle centered at 0, because we're saying z bar is equal to r, but we don't know where z is. So z bar could be, or z could be any complex number, and it has a modulus of 2. So really we're graphing an infinite number of z's, depending on what their argument is, all with a modulus of 2. And if you add all of those together, we call this a locus. It becomes 2, or a circle with radius 2. So on the Argand diagram, sketch the following. We're going to show both the geometric and an algebraic method. The geometric is just realizing that this is a circle of radius 2, but the algebraic method is going, okay, well, mod z is root x squared plus y squared equals 2. Square both sides, x squared plus y squared equals 4. And of course that's a circle, center 0, 0, radius 2. Okay, I might go down to this one here, part C. I'm not going to show an algebraic method for this one, it's going to take too long, and as we get better at this, we have to realize how to do this without replacing it with x plus iy. What we always have to do, though, is make sure we factorize out a negative, because the only way we can determine the center of the circle is if it is factorized in this way. So there has to be a minus here out the front of some brackets. And if there's not, you need to add it in, which means the centre is going to be negative. So the centre of this circle is 2 plus 2i. And we're actually graphing two circles. We call it an annulus. And the first one has a radius of 3 and the second one has a radius of 4. Right, so 2 plus 2i is going to be here. Now, both of those radii are... both of those points are less than 2 because we've got 2 plus 2i. So both of our circles are going to be, if I just move this down to here, they're going to be crossing the planes. We just aren't sure where. We could find out, but we don't need to. And then the second one is just going to be the same thing but a bit bigger. And this means it's in between 3 and 4, so we're going to plot that we know that. If there was no equals to on the greater than and less than, we draw either one or both of them as a dotted line. Okay. The perpendicular bisector. So the length of the vectors from any point on a perpendicular bisector to the 2 points have the same modulus. So the perpendicular bisector of the points A, B and C, D is this idea here. Now we can prove this idea geometrically, and personally it's my favourite way of doing it because it's the only way I know how to determine with 100% clarity what the x and y intercept is of the line that we draw. So if we have a go, we're going to replace z with x plus iy. So x plus iy minus 2i is equal to x plus iy plus 1 minus I. And then I like to write the real and imaginary components together. And then we're going to square both sides by taking the modulus and squaring it. So x squared plus y minus 2 squared equals x plus 1 squared plus y minus 1 squared. And if we actually expand and simplify that for you, I'm just going to skip a few steps. You get minus 2y plus 4 equals 2x plus 2, which will give y is equal to minus x plus 1. And that, of course, is a straight line with y-intercept 1 and gradient negative 1. So that means its x-intercept is 1. And what we actually have graphed is if we plot the original points, we had 2i. Let me draw a line there. And we had minus 1 plus I. If we take out this negative here, it's z minus 1 plus I. Z minus minus 1 plus I. We'll put that over here. And what we've actually just figured out is this line is actually representing a locus of an infinite number of points where this distance is always the same as this distance. So if we had a look at maybe the point down here, we're saying that this distance is the same as this distance, or down here, this distance is the same as this distance. And this is the idea of a perpendicular bisector, and you can prove it algebraically, which personally for all of the perpendicular bisector questions I do, because often we want to know the x and y intercepts. Personally, I'm not 100% confident in determining the x and y intercepts without doing that, because you have to draw the diagram very, very accurately to just plot them yourself. So I just think it doesn't take very long to do that working there. Okay, the next thing we're going to look at is rays and sectors and arcs. So a ray is a line that starts from a point and continues in one direction. The argument of any point on the ray equals the angle the ray makes with the real axis. There's a lot of theory there which is a bit confusing. We're just going to go straight into some examples. So the arg of z is equal to pi on 3. we just draw the first quadrant. Z, in this instance, we're just always going to treat it as the origin. We can manipulate Z by adding and subtracting things to change where it is. But if not, it's just at the origin. Now we importantly, at the starting point, want an open circle, because we're saying that any point on this ray has an argument of pi on 3. But the origin, the point 0, 0, does not have an argument. It doesn't make sense. If you're standing at the origin, you're not necessarily facing a particular way because you are the origin. So we say like the origin has an infinite number of arguments, or an argument, it doesn't have an argument, because you can't be the origin but also facing a direction. It doesn't make sense. To have direction, you kind of need 2 points, an origin and some other point. That's why a unit vector which gives direction can't be defined as just the origin, because the origin does not make sense to have direction. Okay, part B, the argument of Z is between negative pi on 4 and pi on 3. Noting that it's not less than or equal to negative pi on 4, it's just less than. Draw an open circle at the origin. We want to draw a line up here at pi on 3, going on forever, and a steeper line at negative pi on 4, which is going to be at 45 degrees down this way, 135. Doesn't matter how long they are, as long as it's clear what you're trying to say. And I've also making sure that I'm making this a dotted line here. And then we can just shade in that area there. Okay. The last one for our rays is we're actually moving this coordinate here. Now, very importantly, we need to factorize out a negative so it's in brackets. It's not necessarily in brackets here. The negative has to be in brackets, which would give 2 minus 2y, because if you expand through that negative, it's going to be the same thing. And this is telling me my open circle, or the starting point of my ray, is going to be at the coordinate 2 minus 2i. So we've got an open circle there at 2 minus 2i. I'm going to draw a line across here to represent my real axis. And I'm going to draw my ray going up here. There's no inequality here, so we're just saying any point on this line has an argument of 3 pi on 4. And that, of course, is the coordinate, or the vector. We could say a coordinate, which is 2 minus 2i. Okay, we're now going to move on to arcs on the Argand diagram. This is technically not in the syllabus because circle geometry is not in the stage 6 syllabus, but it is in the stage 5 syllabus, so it may appear maybe. We don't know, so everyone teaches it. Okay, so if we want to sketch z minus 2i on z plus 3 equals 0, I like to do this visually. Remember, 0 is equal to 2 pi. So imagine you're standing at 2i, standing at the point 2i, or 3. You've got 2i, or negative 3, that should say, and you turn around 2 pi. In other words, you've done a 360. If you start walking, you're walking in the same direction. So you're starting here and facing that way, and you do a 2 pi, or a change of 0, you're not turning around at all, or you're turning around by 2 pi. You're facing the same direction, so you're walking away. Same idea here. If you're facing this way and then turn around completely or don't turn at all, you're facing the same direction. So that's our graph there, making sure we have open circles at our starting points, and we often draw a little dotted line in between to represent that this and this are at the same angle. Now I do this one visually again. My diagram, I think I must be drawing this one. So we do the same idea. We draw our complex, or our Argand diagram. We go, this is my imaginary axis, this is my real axis, drawing arrows on either end. And we've got 2i and minus 3. But this time, if you're facing this way and you turn around, well, by pi, or 180 degrees, you're now facing that way. And same idea here, if you're facing that way and you turn around by pi, you're now facing that way. So it actually just looks like a solid line like this that doesn't go on forever. Okay. Last one, this one's a bit strange. And this one is the one that we're not sure could be examined in the syllabus. We don't know. So when we're drawing circles, these ones actually represent circles. It's a bit funny. When we're drawing these, we're going to imagine these hints. Imagine you are literally standing on the second listed point and facing the first point. If theta is positive, the thing it's equal to, then the circle or arc is going to be on the left. And if it's negative, it's going to be on the right. I'm going to have a look at that. So I'm going to draw our 2 points. We've got -1 and -4. -1 and -4. And I can't turn, I wonder if I can turn this page. No, I don't think I can. But if you're standing here and facing that way, if you're standing at this point and facing that way, well, since theta is positive, this is going to be the left. So the circle goes on the top, and it's going to look something like this. We just draw, we want to draw some lines in between these two, so that the angle here, that kind of looks like 90 degrees, so I might have to make it a bit taller. I want it to be pi on 3. And then if we try and draw a circle, we're going to draw a circle between these points. It's going to look like that, and then come down here with a dotted line a bit there. If the angle was pi on 2, well, it's clear that those lines wouldn't have to be as tall because we want a right angle there. So the circle might be more looking like that. But since pi on 3 is a smaller angle, we need to make these a bit steeper. That's pi on 3. And then, terrible at drawing these. It looks something like that with our dotted line there. Okay, and that's all you have to do. They're very easy, but we're not sure if they're in the syllabus, so I guess it's important to know how to do it. Sometimes they like to put the center of the circle here, and then from your knowledge, if you did circle geometry in year 10, again, if you didn't, it's fine. This is the only thing you need to know, that there could be a question. There's 2 pi on 3. One of our circle geometry theorems is that this angle here is double that angle. And then to finish off, I just need to make those open circles, and I'm done. Okay, thanks for watching.